All right, I want to welcome you all back for the second module in my set. And this one is going to focus on a case study on flow battery electrolyte optimization. And in this module, this short module, I'll give you a brief intro to flow batteries, very brief. I will follow that up with a little bit of our philosophy and dataset design and the types of parameters that we're going to end up using for our multivariate correlations. And finally, I'll spend a fair bit of time on how we use these correlations to develop a new electrolyte that's much improved. I want to highlight really quickly that this work was done in collaboration with the Sanford lab at University of Michigan. Melanie and I have been working on a number of projects related to this, and it's been quite an exciting and fulfilling experience. So first, I want to tell you a little bit about a flow battery. And essentially, a flow battery is you take something that can be reduced in an organic molecule called an analyte, or something that can be oxidized, another organic molecule called catholyte. These two molecules are stored in tanks, okay, and that's depicted here. And these tanks are connected to a electrochemical cell by which you flow the electrolytes in one direction to charge them or discharge them. And in a flow battery, what you want to do is take some sort of renewable power source, such as photochemical, so solar cells of some sort, or wind power, and convert that into electricity. And the electricity then is used to charge the molecule, and you store the molecule in a tank, the charged form. And then that is released through running the flow battery backwards. And so you can use the energy as you wish when the renewable source is no longer operational. Again, wind and sun are great examples of this. So some of the requirements for a flow battery electrolyte is they have to be stable, relatively so, in the charge to discharge states. And you want the redox potential, the energy density is correlated to this, to be as high as possible. And you want the difference here to be as great as possible. And so we're going to be looking at organic electrolytes, and mainly because with an organic electrolyte in an organic solvent, you have a much greater window by which you can have an electrochemical cell, so you're not limited by water oxidation issues that surround flow batteries and aqueous solutions. So with that as a backdrop, what you want to first do is find a candidate molecule class. And I'm sorry, there's some weird PDF formatting issues here, but you'll still get the general point. And the candidate class that we're going to look at are these electrolytes developed initially by the Sanford lab. What's nice about these electrolytes, as you can see by this CV, is they have nice, beautiful reversible cycling in the CV platform. And they have two two redox events, one to give you the radical here from the initial cation, and the one that actually gives you the formal anion here, and this can be reversibly cycled. For the purposes of this study, I'm only going to talk about the radical stability. Unfortunately, this parent molecule that they originally reported in a JACS paper in 2015, if you cycle it, that means you charge and discharge it a bunch of times, you'll note that it has a flat curve here, but very rapidly decomposes over 100 cycles. And if you want to, let's say, apply a molecule of this sort to a flow battery, these things have to be stable to tens of thousands of cycles, if not more. And so this is clearly not going to be an effective molecule. So the question that we wanted to ascertain in our collaboration was, how do you develop a workflow to optimize this using some data science tools? And so what we initially did was design a training set. And I don't have to go through what a training set is in this video, it's in other videos, but nonetheless, we designed the training set as one would, I think, historically have designed such a training set, by which we looked at initially a Hammett series. You can see that here with some funny business. This is an orthosubstituted methyl, which is not allowed in Hammett, but in our case, you're going to see we can easily correlate it. And we measured the redox potential, which is here, and then this K-rel. Now, this is the relative rate of decomposition. So the larger the number, the more rapidly it decomposes. So you can see the molecule I've highlighted here is the one that decomposes the fastest, at least in this set of experiments. And so initially we see that there's a correlation of redox potential. And just to really clearly show this, redox potential, so you can see it goes down here to K-rel. Okay, so that's something we'll come back to in a second. But there's one place that this doesn't occur in our first sets of molecules that we evaluated, and that is here. So you go from ethyl to isopropyl to T-butyl on this set of molecules. You'll note that redox potential doesn't change. The alkyl group really dominates this, it seems. However, the K-rels are significantly different, and this is highlighted, as you can see here, by this rather exciting result where the K-rel is 0.49 relative to the rest of them. It's the best one on the screen. So these have similar potential and increased persistence. And so one of the first hypotheses which helped us develop the parameter set that I'll briefly talk about is the fact that this radical, okay, is in resonance into this position here. Whoops. This position here, and therefore perhaps that T-butyl is protecting that position from potential decomposition pathways, which would be a dimerization. I should note that the decomposition of these molecules turns into black tar, so we are not really easily able to ascertain what those molecules look like, which makes this harder to evaluate. All right. So we build a statistical model, and I'll make a long story short because this work is published. And the statistical model has two parameters. This is actually really nice to analyze. It has the computed E1/2. This is something we can easily compute using DFT. And then it has this interesting feature called HST that we've named here. And essentially HST is describing that substituent off the nitrogen right here and its height out of plane in its lowest energy conformer. And what I think we initially established when we started thinking about this is E1/2 is purely a thermodynamic term. It's the electronic aspect of this molecule, and that's something that is important for this correlation. But more interestingly, the HST is describing the kinetic stability. Essentially, does it dimerize or decompose in some sort of form like that? And this is a purely steric derived parameter. So we've separated in the statistical model an electronic and steric component. This is not terribly usual for the group, but it's a nice example of it. And we've also separated the thermodynamic and kinetic aspects of stability in these molecules. What that allows you to think about, as you're going to see in the next set of slides, is that thermodynamics and kinetics can be independently optimized to some extent. And so the first thing you do when you do our workflow is you do what we call an interpolation to validate the model. And what we did here is kind of go a little far off the Hammett molecular structure and just looked at this mesotyl substituted compound. You can see we do a reasonable job of predicting that. And then we just do another example where we put it here. So interpolations work. So interpolations in general, this is for your information, are much easier than extrapolations. Okay. The next thing is we do an extrapolation. I will point out that we do a virtual screen first before we do an extrapolation. So we had computed these molecules before we made them. And then we saw very quickly that especially this blue molecule here, which is highlighted over here, that extrapolation is quite far out. It's actually 1,000-fold increase in stability. Note that this is a delta G double dagger as the axis. And we go from molecules that are on the order of weeks in terms of half-life to molecules now that are stable in terms of months. And I should note that Christo, the main postdoc on this study, who's now a professor at Ohio State, what he was able to do was to crystallize this radical. So this radical is actually stable enough to get X-ray structures of. So one issue with this initial correlation that I'll briefly describe here is something I mentioned earlier, and that is that redox potential, so you can see that here, is correlated to half-life. Okay, it's not a perfect correlation. There's certainly some outliers here. And so our best molecule, while it has incredible stability, it doesn't fulfill what you really would want out of this molecule. You want high stability, and then you want also high energy density, which is related to the redox potential. So how do you move from here to there? And I should note, for those of you who don't think about electron volts very often, that the difference here of 0.1 electron volts is essentially 2.3 kcals per mole. So if you think in terms of kcals per mole, you know, this is essentially almost 7 kcals per mole difference in energy if you could put one right there. We don't quite get there, but we do a pretty good job. So we went back to the drawing board and did a virtual screen, and nothing we screened initially with the parent pyridinium structure worked. And again, I'm sorry for this PDF conversion issue here, but nonetheless, one of the molecules that came out of our virtual screen is when we started substituting the pyridinium at new places, especially about the nitrogen, we saw this really interesting increase in potential. That is, if you can't see here, that is 1.23 volts. And that is in the range we wanted. And what this also molecule virtually screened at is a pretty good stability, as I'm going to show you on the next slide. It's not quite as stable as the dimethyl compound I showed you previously, but it is pretty stable. And so when we make these molecules, we actually extrapolate this one. Okay. We also made a second molecule that I'll get to in a second. So first off, the prediction of this molecule with the two methyls is excellent. And all we have is an ethyl here now. Okay, it's excellent. And this is honestly the parent molecule that we chased down for a while when we were trying to develop batteries. We have now new generation versions of this that I won't speak about today. But what I want to point out is the last piece of data in this module is the difference between methyl and ethyl. And if you look at the stability, this is almost 2.5 kcals per mole differences in stability. And that is not a small number, as you've learned in your physical organic classes at this stage. The one really interesting point is ethyl versus methyl is something when you teach, let's say, a sophomore organic class, you try to avoid talking too much about because it's subtle. In this example, it is not subtle at all. And the reason for that is, if you think about it, is that ethyl, one second, is that ethyl can gear out of the plane. So this is going to be coming out at you. There we go. And that is dictated by these two side chains. So this is coming out of the plane. Whereas methyl cannot do that. So methyl doesn't have it. So that just that gearing of the ethyl group out of the plane presents it as a much larger substituent, and that's connected to the HST, the height out of plane. So hopefully I showed you in this module a very brief explanation of how we use our workflow in the applications of flow batteries.